This is the back page of the 3.7 optimization worksheet number 1. We're looking at number 5 here. Highway 400 average 54,000 cars per day for its first 5 years, charging 50 cents per car. Scientific research study concludes that for every 5-cent increase in toll, the number of cars will be reduced by 500. In order to maximize revenue, what toll should Highway 400 charge? All right, so for these types of problems, once you see the pattern, you'll be able to kind of recognize it and apply it for each of these types of problems. So the idea here is that rates, we can think of the rate as the change in revenue times the change in the number of cars. So let's kind of piece this together here. So the toll starts at 50 cents, but for each increase of 5 cents, there's going to be an equal effect in the number of cars that's going through the toll. So each 5-cent increase, then we're gonna lose 500. So that means if we have two increases, then we're gonna lose 2 times 500, which is 1,000. So it'll just keep continuing here. So the idea here is that obviously if you charge more per car, then potentially you're going to increase your revenue. However, if you keep charging too much, then you're losing business along the way, even though you're getting more toll amount from each car. However, there comes to be a point where it just doesn't make sense to keep increasing charges if you're losing this many cars going through. So the idea is, where is that balancing point? What's the optimal amount of toll increases so that we can maximize revenue? All right, so this is the equation that we're going to be working with. So notice that everything's in terms of x. We really just have to find the derivative and set equal to 0. So we could go through product rule, but I think maybe it's easier to just expand everything out and just use power rule. So if we expand everything out, distribute 0.50 through, distribute the 0.05x through, so this is the result. Just using our calculator, we can combine like terms here. And then I'm going to rearrange this in decreasing order of degrees. So negative 25x squared plus 2450x plus 27,000. Here's our equation that is now set up and ready for power rule. So we can now go through derivative. So go through power rule. Negative 25x squared becomes negative 50x. 2450x becomes 2450. 27,000 goes to 0. We just set our derivative equal to 0. And then we solve for x. We get x equals 49. So this tells us that the maximum revenue will occur if we increase the toll 49 times. So if we increase the toll 49 times, it'll be 49 times 0.05, which is $2.45 plus 50 cents, which is $2.95. So maximum revenue will occur if we're using these restrictions. It'll be maximum revenue will occur if the toll is at $2.95. All right, number 6. The manager of a department store wants to build a 600-foot square foot rectangular enclosure on the store's parking lot in order to display some equipment. 3 sides of the enclosure will be built of redwood fencing at a cost of $14 per running foot. The 4th side, again, that's misspelled here, F-O-U-R-T-H. The 4th side will be built of cement blocks at a cost of $28 per running foot. What dimensions will maximize the total cost? So we're trying to minimize the total cost, and then try to find the minimum cost and also find the dimensions of this enclosure. All right, so I'll let here's our rectangular enclosure. We'll let the horizontal be x, we'll let the vertical be y, and the cost equation is simply multiplying each of the dimensional lengths by the amount that each running foot is going to cost. So we know that three sides will be 14, and then one side will be 28. So if we combine those terms as 14y, 14x, 14y, 28x, combine those together, combine like terms. So here's our cost equation, 42x plus 28y. So normally we could, our goal is to find the derivative of cost equation, right? We're trying to minimize cost, so we're trying to find the derivative for cost. But before we do that, we have to get our equation down to one variable. So we have to basically use another equation to help us through that. So the other equation that we can use is going to be area, because we're given information about area. We know area is 600 square foot. We know area of this rectangular enclosure will be length times width, which is x times y. So area is x times y. Replace a with 600. And I'm just going to go ahead and try and get our equation in terms of x. So I'll solve for y. If I solve for y, y is 600 over x. Replace 600 over x in for the y. And then now I have my cost equation down to one variable. 42x plus 28 times 600 over x. Combine, we can clean this up a bit. We get 16,800 x to negative 1. Now our cost equation is ready and prepared for us to apply the power rule. So we can find the derivative now. 42x becomes 42. 16,800 x to negative 1 becomes negative 16,800 x to negative 2. And then we set that equal to 0. We set our derivative equal to 0 to find our critical point. And then we rearrange this to solve for x. X squared equals 16,800 over 42, so x equals 20. So when x equals 20, this is going to be the minimum, the dimension for that will allow the cost to be at a minimum. So if x is 20, we can solve for y. We know the area equation is 600 equals xy. Replace x with 20 and then solve for y, so y must be 30. So the dimension is going to be 20, length of 20 and width of 30. And then finally, to find the cost equation, to find the minimum cost, we can just plug these optimal dimensions into the cost equation. So 20 in for x, 30 in for y, and the cost, minimum cost will be $1,680. All right, number 7 is going to be similar to what we did with number 5. Let's see, 150 room hotel resort is filled at a rate of $125 per day. For each $5 increase in room rate, 3 fewer rooms are rented. What room rate will result in maximum daily revenue? So revenue is going to be the product of room rate times price rate. So the cost is $125 for initially, and then they're trying to test out this $5 increase. But the problem is that each time they have a $5 increase, whether it's 1, 2, 3, however many times they do a $5 increase, they're going to have the same thing happen here, where it's going to be an equal effect in the sense that there's going to be 3 less rooms rented out. Okay, or 3 less client or customers here. So here's our formula here. So for each $5 increase, there's going to be a loss of 3 rooms rented. Okay, so now it's just a matter of expanding everything through and then trying to get our equation set up and ready for power rule. So distribute everything through. We get negative 15x squared plus 375x plus 18,750. So here's our equation, which is ready, set up, ready to go for derivative, going through power rule. So to find our prime, negative 15x squared becomes negative 30x. 375x becomes 375. We set our derivative equal to 0. We get x equals 12.5. So 12.5 is not going to quite make sense, because this is saying that we're going to that the optimal situation is if we or if they raise the rate 12.5 times. So this doesn't make sense, right? Can't raise the rate 12.5 times. So we're going to just pick the closest whole number to 12.5, which is 12 and 13. So which will produce the better revenue? Is it going to be at 12 rooms or 13 rooms? Well, we can test that. We'll just plug 12 into R of X, plug 13 into R of X, and see which one produces the higher revenue. It just so happens that 12 and 13 both produce the same revenue, so that means optimal situation will occur either on the 12th or the 13th rate raise. They're both both 12 or 13 rate increases will produce the maximum revenue, because before 12 or after 13, the revenue optimal revenue will begin to decrease. All right, so the room rate must then be 125 times 5 plus 5 times however many rate increase. So we can either do 125 times 5 times 12, which is 185, or the next increase up, but I just had it as 185. Okay. All right, last one here. This is a problem that deals with perimeter and area. So a farmer has 400 feet of fencing to make 3 rectangular pens. So here's the full rectangular area, and then we have 3 rectangular pens. So this is one rectangular enclosure, enclosed region, and then here's the second, and here's the third enclosed region. I'm just going to assign this entire horizontal as X and X, and then all the vertical as Y's. Okay. All right, which dimension of X and Y will maximize the total area? So we're trying to maximize area. We're trying to get the area equation down to one variable, find the derivative for the area, and then find the critical points from the area equation. All right, so area is X times Y, so the entire length of this dimension of this enclosure is X times Y, so that's the area. But the perimeter is a different story. The perimeter is going to be a number of fencing. So the fencing is going to be every line that we see here. So it'll be 2X plus 4Y. So 2X plus 4Y. We know the amount of fencing is 400 feet. So we can now use this equation to get our area equation down to one variable. So again, I'm going to solve for Y. We're just used to seeing x's as our variable here. So we'll solve for y. So subtract 2x, divide by 4. We get 400 minus 2x over 4 is equal to y. Plug this expression in for the y of the area equation. So x times y, 400 minus 2x over 4. All right, so now we want to try to clean this up before we find the derivative. So distribute the x through, and then divide by 4. We get 100x minus 1/2 x squared. Here's our area equation. We find the derivative. 100x becomes 100. 1/2 x squared becomes x. We set our derivative equal to 0. We solve for x. X equals 100. So to create the maximum area will be x. Will be when the x is equal to 100. So when x equal to 100, we can use this equation to solve for y, because we're trying to find the other dimension for the other for the width. So if we plug 100 in for the x, we can solve for y. 400 minus 200 is 200 divided by 4, which is 50. So the optimal dimension to create the maximum area, given the restriction of the amount of fencing and the formation that this has to create, will be 100 feet by 50 feet.